Okay, we're back to our usual schedule this week. We have the homework going, right? We've got the assignments that are due before class on Monday. We've got SI sessions. We have UTF office hours. And we are now progressing from chapter 16, which was on resonance and reactions of dienes, to benzene and aromatic compounds. So we're kind of just stepping up and applying what we learned about resonance to a different type of molecule. Okay? We'll first learn about benzene itself, a little bit about the history. This is kind of a pivotal molecule. It's also what I kind of think about as being the prototype molecule for a whole class of molecules that are called aromatic molecules. Okay? So then we will talk about the criteria for being part of this aromatic club, right? The elite club for molecules to be a part of. And we want to be able to then apply that and recognize various other molecules that may look a little bit different than benzene, but they can be included as aromatic. All right, I have the rest of the exams. If you haven't picked it up yet, you can get it after class. Any questions on where we're at, where we're going? All right, let's do a clicker. All right, so the first thing we're going to do in this chapter, we're going to talk a little bit about benzene, leading to us coming up with some criteria for aromaticity. So let's think about benzene. We might know what it is already, but this was kind of an unusual molecule early in the study of chemistry, or not way back, but in the 1800s, basically. And remember, at that point in time, they didn't have NMR and mass spectrometry and all these cool techniques that we have now to determine structure. So basically, they were able to, through maybe combustion analysis, so burn the molecule up and see how much hydrogen and carbon comes off, to determine a molecular formula. And that molecular formula, the one that they came up with, is this C6H6. So right off the bat, if we were trying to determine the structure of a molecule with a formula like that, what would it tell us?
4 degrees of unsaturation.
Yeah, there's lots of unsaturation, right? Lot of unsaturation. All right. In fact, like it was suggested, 4 degrees, so 4 sites of unsaturation. So some of the early ideas for the structure, look kind of crazy for us now. They were proposed things like this, with 2 double bonds, right? So this has the right formula. There were some other ones I was looking. I just got some of these structures off Wikipedia this morning. Look at this one. Has this 6-membered ring, but they have bonds across. This one's back behind, and this one's back behind. Right? So I don't know how you'd even make a 3-dimensional molecule of that, but that was one of the ideas. Another one was kind of like 2 triangles like this. Right? So there was a lot of different ideas that were kind of crazy, but then we start to put in some more data here, and some of the information that was gained is that all of the carbon-carbon bonds in benzene, they're all equivalent to one another. Okay, so we can rule out some of these, at least the one on the left. The other 2, I don't know about that middle one. I just can't get it. I just can't imagine it yet. The one on the right looks like they're all basically about the same. all the carbon-carbon bond lengths are also, the lengths are equivalent. So if we make a structure with double bonds and single bonds to create unsaturation, all of those bonds are the same length, right? So we know that usually carbon-carbon double bonds are shorter than carbon-carbon single bonds. Okay, so that's kind of weird. And all of the carbon-hydrogen bonds are also equivalent. Okay, so there has to be lots of symmetry in this molecule. The other thing that was discovered that was very unusual is the reactivity of benzene. So we know that if we have alkenes, common reaction with alkenes is to brominate it, right? An electrophilic addition reaction, you learned that before. This was actually used as a qualitative test for the presence of alkenes. So bromine itself is orange. You drip it into a solution with an alkene, it adds to the double bond, and the orange color goes away. So this loss of color was as a test for the presence of an alkene. But if you do that same reaction with benzene, it gives no reaction. Right? So what if you were trying to figure out this structure, you thought, oh, I'm going to put all these double bonds in it, and then you do the test for double bonds and it says, oh, no double bonds. Right? So that would be kind of, I don't know, it would be hard to figure out. So what they did figure out, though, that if they took bromine and they added a catalyst, they could get a reaction to take place. Okay? And when this reaction took place, though, it didn't do an addition reaction. It did a substitution reaction. Okay? So it had completely different chemistry. And then, in fact, you could do this reaction again using the catalyst. And it could add again C6H4Br2. But in this case, you don't get a single compound, but you could get a mixture of 3 discrete molecules. Okay? 3 distinct molecules. All right, so they had to come up with a structure that fit all of this data. Long time, we'll jump right to the meat of it here. And so, in fact, the kind of the story that goes along with this, and I don't know if it's true or not, this chemist, I think it was Augustus Kekule or something like that. That's his last name. I don't know about the first name. I might be making that up. But he was working on this structure, trying to figure out how to come up with a structure for this. And probably the wide folk tale or something is that he had a dream in the night, and he had a dream of this snake, and it reached back around and bit its own tail. And from this idea that it was in a ring, this snake in a ring, he came up with the structure of benzene. Who knows whether we should believe it or not, but it's kind of cool. So here's a structure of benzene as we often draw it up on the left. Okay? And from this structure, what we could, I think I even showed this the other day, if we just push these pi bonds around in a circle, we can come up with another structure. Okay, so this other structure looks just the same, except the double bonds are just in the opposite positions. Okay? And for a long time, this was thought to be an equilibrium process. We have 2 different structures that are basically going back and forth. But if that was true, then the ring should kind of be puckering and stuff because the double bonds should be shorter than the single bond. So it should be flexing and, doing things like this, right? So that wasn't observed, and so it's known now that this is, instead of being equilibrium, this is resonance. Okay, so neither of those structures are the real structure, but the real structure, the hybrid structure, we could draw something like this with dashed lines, if I could get my pen to draw these around in a circle. So we have partial 1.5 bonds between each of those carbons. So this fits back to the idea that all of the carbon-carbon bonds are the same. All right? So this would be some kind of hybrid. Sometimes you see benzene just drawn with a circle in the middle. Okay? We're not going to really use this type of structure because when we draw reactions and we push electrons, it's easier to do that if we have discrete bonds. So we're going to draw one of the two resonance forms, okay? So we're not going to use this one really. Use. Okay? But you'll see that places, all right? Okay, so we can also understand the resonance. So if we have this kind of structure, right? So we have then hydrogens that come off of each of these carbons. What would the hybridization then be for these carbons? sp2, right? So the 3 bonds that are being shown from each carbon to 2 other carbons and to the hydrogen are all to sp2 hybridized, using sp2 hybridized orbitals. And what do we have left over then? We have 3 sp2s, we have a p orbital left over. Okay? So because it's sp2, the molecule is planar, and each atom in the ring has a p orbital. Each of those carbons can donate 1 electron into this now pi system, and essentially these electrons can cycle or can spread all the way around this ring. Okay, so it's basically shared equally around the ring. So sometimes you see it drawn with like a little donut on the top and the bottom. Okay? So this is kind of the hybrid structure, right? This would kind of equal this up there. Okay? Other related compounds as well. So, here's benzene right here. Here's some other molecules across the top that have benzenes kind of incorporated in the middle. Right? This molecule here is called vanillin or vanillin. Comes from vanilla beans. This has the smell, taste of vanilla. All right, this is partly where this original aromatic came from, that some of these plant metabolites had these nice aromas. Okay, so this is vanilla, comes from vanilla beans. This is called cinnamic acid. Carboxylic acid comes from cinnamon. Okay, so that's the smell of cinnamon. We can also link benzene rings together to make kind of larger aromatic compounds. This one here is called naphthalene. Okay, and if you've ever smelled it, this is, I don't know who it, well, somebody told me they did one time. I don't know whoever uses this, but they're in mothballs. So I don't know if you've ever smelled that smell. It has kind of a characteristic smell. And this bigger one over here, this one is called phenanthrene. Okay, and they can get even bigger, these kind of polycyclic aromatic compounds. Right? And as you would notice, each of the carbons around these rings have You know, they're all sp2, they all have p orbitals, and so we have this big system of sp2 hybridized carbons. All right, so what do these all have in common then? What makes it, if these are all aromatic, what does it take to become aromatic? All right, so there's a couple of things. So I've got it listed as two main criteria here. The top one is that it must have an uninterrupted cloud of pi electrons. Okay, so that means that it has to be cyclic, it has to be planar, and it has to be completely conjugated. So this means that it has to have a p orbital on all atoms in the ring. Okay, we saw before you could have different substituents attached, and those don't affect whether the ring itself is aromatic. Okay, so it's got to meet those three criteria. The fourth one, or the second big one here, is that there has to be a certain number of pi electrons, or certain number of pi bonds, certain number of pi electrons. And we can count these in either of two ways. We can either say that the pi cloud from above has to have an odd number of pairs of pi electrons. So we're looking at pairs, odd number of pairs, or we can use this thing called the Huckel's rule. This says the number of pi electrons has to fit this formula right here, where n can be any kind of integer number. So if we write these out over here, we could have an n value, and we could have the number of pi electrons. We could start with 0. So if we put 0 in for n, we get 2, right? So we could actually have an aromatic compound with only 2 pi electrons in it. If we put n equals 1, 4 times 1 is 4, plus 2 is 6. N is 2, 2 times 4 is 8, plus 2 is 10. We could go up to 3. 3 times 4 is 12, plus 2 more gives us 14, and so we could keep going up like this. So these are possible numbers of pi electrons that could make a molecule aromatic. Okay, so let's look. Well, let's start with benzene over here. All right, so for benzene, we could either count the number of pairs of electrons, which means kind of counting the number of pi bonds. So we'd have 3 pairs, right, of pi electrons. So we get an odd number of pairs. However, we know each of those pi bonds represents 2 electrons. So 2, 4, 6, we have 6 pi electrons, right? And so that fits one of the possibilities, right? Okay, what about naphthalene? We count the pairs, we count the pi bonds, 1, 2, 3, 4, 5. We got 5 pairs of pi electrons. 2 times that, we have 10 pi electrons. That also fits. Okay, it's just the next one up. If we look at phenanthrene, we have 1, 2, 3, 4, 5, 6, 7. We have 7 pairs of pi electrons, so that gives us 14 pi electrons. That also fits. Okay, so all 3 of these are aromatic. They're planar. Yeah, question?
Do we know what N represents if we're just given a molecule? Or is this
And it just gives us a series of numbers which could fit. Okay? N doesn't really represent any property of the molecule. It's just a number we can put into this equation and come up with a series of numbers of pi electrons. Okay?
It's just a rule that...
Right. It's just kind of an empirical rule that they came up with to fit the data. Right? All the aromatic compounds had either 2, 6, 10, 14, 18 on up numbers of pi electrons. Okay?
Quick question.
Yeah.
So in the case of a carbo anion, how would that work? So it said like instead of that double bond there, we have like a carbo anion.
Yeah, let's wait and we'll get to some other, deviations of this, right? Okay, so, if you have matter, of course you need to have antimatter. If you're watching Star Trek or something. If we have aromatic, we could also have anti-aromatic. All right? So anti-aromatic compounds have to meet all of these same criteria. However, they have an even number of pairs of electrons. So Huckel's rule says anti-aromatic compounds have 4n pi electrons rather than 4n plus 2. Okay, so again, if we had n, we had the number of pi electrons. We could have, that's 0. I don't know if we can have one with 0 or not. Seems like it fits in there. 0 would be 0. 1, it gives us 4. 2 gives us 8. 3 gives us 12. So these numbers, if we have a molecule, it's cyclic, has a p orbital in every orbital, and is planar, and it has one of these numbers of pi electrons, it's said to be anti-aromatic. Okay? What we'll see is that aromatic compounds are very stable. That's why benzene doesn't have the normal reactivity. Anti-aromatics are very unstable. Yeah, question?
So aromatics are generally classified by that property they have of smelling, being aromatic. Is there like a physical property to anti-aromatic?
Well, okay, so I think aromatic, actually our technical classification doesn't really have to do with the smell. Maybe that's what they first, the first ones maybe were discovered from plants like vanilla and things like that. But, I don't think that naphthalene has a particularly nice smell. And there's some other ones that we'll see that I think would have a downright terrible smell that I'll show you. But it's really what it is this unusual stability and a unique type of reactivity that makes something aromatic. Okay? And all of the molecules that have that same properties or have the same physical properties, chemical properties, follow these rules. If they're anti-aromatic, the thing is anti-aromatic are very unstable. So in fact, I think it's very hard to actually make anti-aromatic compounds because they're just too unstable. Right? So I think it took a very long time. So here's just cyclobutadiene. It took very long time, even though the theory said this should be anti-aromatic, to actually make a molecule that looked like that. And they couldn't make just butadiene. They had to add like benzene rings and different things onto it, different substituents to actually be able to make it. All right? And if you so look at this one, we'll talk more about ions, but this is a 5-membered ring, and it has 2 pairs of electrons. This would have 4 pi electrons, so this should be anti-aromatic. Look at our stop sign molecule here, right? Cyclooctatetraene. We think, okay, that should be anti-aromatic if it follows all this, but you can actually make, or this molecule's known, however, it's not planar. If you look at it, it actually makes this kind of bent structure like this. All right, so instead of becoming anti-aromatic, which is so unstable, it just bends out of the plane to avoid that. And it's, even though it doesn't have the conjugation now because it's not planar, it's still more stable than being anti-aromatic. Okay? So a molecule doesn't really want to be anti-aromatic, right? Because that's a super unstable situation. Yeah?
How would we predict the geometry of that molecule? I mean, just looking at it planar, I mean, on paper, I'd have no clue that it's that.
Yeah, neither would I unless I read it in the textbook. That's one way you could do it. Yeah, I don't know. There's computer programs that can calculate and predict three-dimensional structures of molecules, right? I think in general, if these molecules, if we know a certain combination of physical shapes and properties like this makes it super unstable, then it's probably going to try to do something which makes it more stable, right? Molecules are always searching out or adapting their shape or their hybridization to be as stable as possible, right? And so, I would think of this anti-aromatic kind of being at the transition, the maximum of energy rather than minimum where molecules tend to seek, right? So yeah, it's a good question, but yeah, I don't know. All right, so let's look at some other molecules and let's try to decide whether they could be aromatic or anti-aromatic or non-aromatic. So those are kind of the three possibilities we have. All right, so what about the one on the upper left? Do you think that's aromatic or not? No. So this is not aromatic. Why not? It's not what? Upper left.
It's not cyclic.
Well, the upper left one is cyclic, right? It's in a ring. This one here, right? The other left. It doesn't have p orbitals on all of the carbons, right? Because this position right here, is sp3 hybridized, right? So just like other conjugated systems, conjugated versus isolated pi bonds, if it's split or interrupted by an sp3 hybridized atom, right, there's no p orbital there, so we can't have resonance all the way around the ring. All right, what about the one in the upper middle? So this nitrogen, when nitrogen has 3 bonds, remember, it always has a non-bonding pair of electrons if it's neutral. What do you think about that one? Is that aromatic? Yeah? How many people think that one's aromatic? Raise your hand. Okay, quite a few. How many people think it's not aromatic? Okay, a few. So what's the question here? What do we have to decide? Right, we got to know where is that lone pair residing, right? Is it in the pi system or not? Okay, so where do you think, what orbital do you think that non-bonding pair of electrons would be in? The what one? Okay, so what orbitals do we have around that nitrogen? Right, what's the hybridization of that nitrogen? Should be sp2. So what possible orbitals do we have? We have sp2 orbitals, right? There should be 3 of those around that nitrogen. And what else? A p orbital, right. So we have to know whether that non-bonding pair of electrons is in an sp2 hybridized orbital, right, which would be in the plane of the ring, or if that pair is in the p orbital, right? So in general, if there's a pi bond already drawn to that atom, that means that atom is already donating 1 electron into the pi system, just like benzene does. All right? So the other pair has to be in the sp2 hybridized orbital. All right, so if we try to draw this molecule kind of from the side, like this, right, we're going to have a p orbital on each of these atoms, and we have 1 on the nitrogen. We also have this sp2 hybridized orbital sticking out here. So if we're comparing this to benzene, what is that sp2 hybridized orbital used for if it was benzene? the bond to a hydrogen, right? But nitrogen has one more valence electron than carbon, so nitrogen has a pair of electrons rather than a single electron, so it doesn't easily make a bond right there. So, in this case, since we already have a pi bond going to the nitrogen up here, that nitrogen is donating one electron into this pi system along with each of these carbons. And so we have 6 pi electrons, right? And the non-bonding pair is out here in the sp2 hybridized orbital, okay? So because that pair is in the sp2, it doesn't add to the number of pi electrons, right? So this one has 6 pi electrons. This is aromatic. Okay, this molecule is pyridine. Pyridine smells really terrible if you ask me. So, all right, so we got one not and one yes. What about the third one? No, that's an easy one, isn't it? Right? It's not even cyclic. All right, let's look at these ones at the bottom here, though. Okay, so in order to figure these out, of course, we need to be able to look at these heteroatoms, right, the non-carbon or hydrogens, and just immediately know how many non-bonding electrons there are. Okay? So how many would there be on oxygen? Right, there's 4 electrons, 2 pairs, right? Just like when we have oxygen in water or in ether or ketone, right? Oxygen has 2 bonds, it has 2 non-bonding pairs. All right, so if this molecule is cyclic, to be aromatic, it needs to have a p orbital on each position. So what do you think? What's the hybridization of the oxygen? Right, we should think that it would be sp3, right? What if I told you that's not true? Right, so remember we talked about last week or sometime when we had like an amine or an oxygen attached to a benzene ring that nitrogen could rehybridize to be sp2 so it could have resonance. All right? So that's essentially what happens here. Even though we would normally think that oxygen would be sp3, if it rehybridizes to sp2, it can put one pair in the sp2 hybridized orbital, just like pyridine did, but it can have the other pair in the p orbital, and then the pi system has 6 pi electrons in it, making it aromatic. Okay, so this is not going to be sp3, it's going to rehybridize to sp2. It actually pushes some of those electrons closer together, which costs some energy, but it becomes aromatic, right? It has to pay this ticket price to become part of the aromatic club, right? And then the payoff is big, right? So if we drew this one from the side, we could draw this like this, right? So all of these other carbons would have p orbitals on them. Those are easy. We see pi bonds to them. This oxygen is going to have a p orbital as well and an sp2 hybridized orbital. Okay? So when we add up all the electrons, so all these carbons are going to donate 1 electron into the pi system. And the oxygen puts one of its non-bonding pairs in the pi system and one of the pairs in the sp2 hybridized orbital. Okay, in that way, if we count up the pi electrons, we have 2 from the oxygen, 1 from each of the carbons, and so we end up with 6 pi electrons. This one is aromatic. Okay? This molecule is called furan. Right? If you add 4 hydrogens and hydrogenate those double bonds, what do you get? Tetrahydrofuran. Have you ever heard of that before? No? THF. It's a solvent. Right? You guys saw that before, I'm sure. Hydroboration, oxidation reactions, and this is a common solvent. Ding, ding, ding. All right, so what about the next one? Look at the next one, has a nitrogen there. 1 pair. This is called pyrrole. All right? This is also aromatic. Yes. Just like furan, except now in pyrrole, this sp2 hybridized orbital is used for this nitrogen-hydrogen bond. Right? And the non-bonding pair is in the p orbital. So you got 6 pi electrons in the ring, makes it aromatic. Okay? So the general rule here is, remember what I said up here on top. If there's already a double bond drawn to that nitrogen, then we know that the nitrogen or the heteroatom is only contributing a single electron into the pi system. If, like furan and pyrrole, there is no nitrogen, there is no double bond drawn to the heteroatom, then that atom should contribute 2 electrons. Okay? So look at this next one. This is called oxazole. The bottom right. Oxazole. You don't have to memorize the name of that. What do you think? How many electrons and how many nitrogen, like always, has 1 non-bonding pair. Oxygen has 2 non-bonding pairs, right? Is that molecule going to be aromatic? How many people think it's aromatic? How many people think it's not? Dang, almost even. Well, what I would say is that, molecules want to be aromatic. If they had little brains or something, they would want to be aromatic, right? If you were a molecule, you would want to be aromatic. I'm just telling you. All right, so if there is a way for that molecule to become aromatic, it will. All right, because it becomes more stable. It lowers itself in energy. So let's look at these pi electrons. So what about these pi electrons? What orbital would those be in? Right? That nitrogen already has a pi bond. So these will be in the sp2 hybridized orbital. Right? Oxygen has 2 pairs, just like in furan over here. So one of the pairs is going to be in sp2. The other pair is going to be in the p orbital. All right? So then that gives us 2 electrons from the oxygen, 2 from the double bonds that are already drawn, gives us 6 pi electrons. This is aromatic. Yeah, question in the back.
Can you explain why the 2 electrons on nitrogen are in the sp2?
Yeah. Well, let's just draw it out. We'll try to draw this out like I did those other ones, right? Okay, so we have the nitrogen here. We have the oxygen like this. Right? We know we have a p orbital here, here, here. The nitrogen already has a pi bond drawn to it here, right? So we know from this structure that it has to have a p orbital, and that p orbital has a single electron, which is part of this double bond. Okay, so this would have a p orbital here, Oxygen's going to have a p orbital. I can't fit all this in here, though. Oh, yeah, it's even next to the edge over there. Oh, all right, so I can't even fit that in. So in this case, so this nitrogen here, I would say, is like the nitrogen in purity, right? It already has a pi bond drawn to it. So we know when there's already a pi bond drawn to it, the non-bonding pair is going to go in the sp2. That's the only place it can because the p orbital already has one electron in it. Okay? The oxygen here can have one pair in the p orbital and one pair in the sp2 hybridized orbital. Okay? So again, it rehybridizes to sp2, which is not what we originally predicted, because it can become aromatic if it does so. Okay? Everybody with me? More or less? Okay, so you can have these expanded rings too. Like, look at these big rings. So when they have these big rings, or they don't have to be big, but when you have these rings with alternating double bonds, they're called annulines. And this 14 or this 10, this tells us the number of carbons or the number of atoms in this ring. Okay, so if you count up the atoms, it has 14 carbons in that 14 annuline. That also means, since we have alternating double bonds, it also has 14 pi electrons. And so that's one of the numbers that fits for aromatic. So 14 annuline is aromatic. 10 also fits the series, so that's aromatic. We talked about naphthalene as well. Look at this big one, benzoapyrene. Right? So if you count all those up, that's also aromatic. Okay? So you can have these really big rings. Not all of polycyclic rings like this, though, add up to the right number of electrons. So in fact, benzoapyrene is something that's produced in tobacco smoke. All right, when you burn it, it produces this. A lot of these kind of compounds are carcinogenic because I'll show you a structure later that you can kind of see it. But if you've all had biology, so the structure of DNA, has all these base pairs that are stacked like this, and it creates these two planar kind of shelves, and these flat aromatic molecules can slip right in between the base pairs. It's called intercalation. And it sometimes can cause then DNA damage and things like this that can lead to cancer. Okay? So that thing is not that good to inhale. All right, so what do we have? All right, so looks like we'll just stop here. So we've looked at the criteria for aromaticity. We've been able to pick out some molecules, determine whether they're aromatic. We're going to talk a little bit about reactivity, and then we're going to do some naming tomorrow. All right, see you tomorrow.